Via your presentation.
Hello, everyone.
So could you show me your slide? Yes, thanks. So now we can start the afternoon session of the second day. The first speaker is Professor Francisco Buscemi from Nagoya University. The title is Fully Quantum-Based Rule from the minimum chain principle. So please start.
Okay, thank you very much for giving me the opportunity to present some of my recent research activities. Can you hear me clearly? Do you see the slides? Everything is all right? Can you confirm?
It's okay, please.
Oh, okay, thank you. All right, so here is a list of work that led to these ideas. So we started working on kind of a reverse bounce in thermodynamics back in 2020 with 3 students. And then these ideas developed into a theory of quantum retrodiction, first applied to quantum statistical mechanics with fluctuation theorems, for example, and then developed into something more mathematical in a sense. And today I will be presenting 2 works along these lines. The first in collaboration with Bai and Valerio Scarani. Bai at the time was a postdoc in Singapore and now is in Hong Kong, in Gwangju University of Technology, which has been published recently in Physical Review Letters, and another work with a PhD student of mine, Nagasawa-san, which is under review and applies these ideas and to the problem of macroscopic states and macroscopic entropy. Okay, so what do I mean by Bayesian inference in this talk? The scope by now is extremely limited. Of course, Bayesian inference is a huge topic in mathematical statistics. But in this talk, we will be focusing on Bayes' rule itself, so the core of Bayesian inference. Let me start with a disclaimer. So what this talk instead is not about. So I will absolutely not touch upon any philosophical debate. For example, the fight between Bayesianists and frequentists or cubists. We will not touch upon those topics at all. So we will be using Bayes' rule really as a tool. Okay, so we are postmodern. We don't care about philosophy or this kind of thing. We just take Bayes' rule as a tool, and we will try to see in which sense it can be extended to a fully quantum version. So what this talk instead is about. So this talk is about the unreasonable pervasiveness, as I call it, of Bayes' rule throughout science. So the formula is this simple one. So as you know very well, you start with a prior distribution on a set of a hypothesis, and then on some likelihood, okay, that tells you that given some hypothesis H, what is the probability of observing data DO, the observed, okay? And by taking the product, you have the joint distribution, so that upon observation of a particular data, DO, the posterior, that is the updated probability distribution on the hypothesis given the observed data, is just given by the joint distribution divided by this proportionality constant. This is something that we learn already probably in high school, I think, and it is usually explained or proved, okay, in scare quotes, proved by using arguments, with urns and colored balls. You have an urn, for example, with some blue balls, some red balls. You don't know how many of them there are. You have some prior distribution over the possible numbers. You pick up a ball at random, you see it is red, and how, you can update the belief about the content of the urn given the data. Okay, typically proofs are given in this way. But the thing that should be surprising in a sense is that even though the world around us is not made of balls, in our head we just don't have colored balls, but we have more complex thought processes, and yet Bayes' rule seems to be a good rule to update beliefs as well, no? So events that are not just balls in an urn. So how comes that Bayes' rule is so ubiquitous in science? And there are some answers to this, but I think that these are all wrong answers. So somewhere you find it written that Bayes' rule is general because it is just a trivial consequence of the law of total probability. Or maybe Bayes' rule is general and you can apply it to physical processes because it stems from the tailed balance or some other KMS balance or whatever. But I think that these answers point in the wrong direction because they give an answer to the wrong question. What is the correct question to ask? So why Bayes' rule provides a good update rule? This is the question we should provide an answer to. So there are possible justifications of why Bayes' rule is somehow the way to update beliefs. One argument follows the idea of consistency. Okay, so Bayes' rule is special among all possible ways to update belief in the face of new data because it is the only rule to be thoroughly consistent. And this is the idea that was initially put forth by De Finetti already more than 100 years ago, and then again put forth by Harold Jeffreys, Savage, Cox, all people that work on the foundation of probability theories. Consistency, what does it mean, consistency? Consistency means that if you don't follow Bayes' rule to update your beliefs, you will basically lose money deterministically in the long run against some bet that you can take, right? This is the Dutch book argument for Bayes' rule. There are other approaches to the validity of Bayes' rule and the generalization of Bayes' rule. The most notorious ones are the framework of probability kinematics by Richard Jeffrey, which is different from Harold Jeffreys, and Julia Pearl's method of virtual evidence, which is based on Peirce's theory of Bayesian networks and can derive a generalization, so to say, of Bayes' rule using this method. So before I continue, I should first of all clarify what this probability kinematics and visual evidence method lead to. It's a slight generalization of Bayes' rule, if you like. In fact, it is the usual Bayes' rule, but with a little twist. Okay, so in fact, in this talk, rather than focusing on the vanilla version of Bayes' rule, I will be focusing on a slightly generalized version of it, which is sometimes called the Bayes-Jeffrey-Pearl update rule. Okay, so how is this defined? So consider a classical discrete noisy channel. Okay, Pi given X is the hypothesis, and I is the data, if you like. And then you have some prior on the hypothesis, gamma X. Now, suppose that you are in the shoes of the receiver and you observe a definite value I0. Okay, so then vanilla version of Bayes' rule tells you that you should update your prior to this posterior probability that we denote here by R gamma p because it depends on the noisy channel p and depends on the prior gamma, which is a conditional probability of x given the observed value, and this is given by the Bayes rule. Okay, so this symbol in the denominator, this p gamma, just means the marginal of this thing, so that you apply the channel to the prior, you marginalize on the input alphabet x, and you get some probability distribution on the data I. But what if the observation instead is noisy and returns not a definite value, but some probability distribution on the data? So the typical example here, for example, that you are doing some noisy observation. Okay, so you are looking at some colors in a dim light room. Okay, so maybe you can say that it is not a white, it is not a black, but maybe you are confused about whether it is an orange or a brown color. Okay, so in this case, you can say that your observation returns you some probability distribution on the data. Okay, some arbitrary probability distribution on the data. So how would you now update your prior gamma x in the face of this noisy data, sigma I? And this is where these extensions, so to say, of Bayes' rule, provided by Jeffrey and Pearl independently. Jeffrey formalizes his probability kinematics in the 60s, Pearl's more than 20 years later, and they don't know of each. Of course, Jeffrey cannot know of Pearl, but Pearl does not cite Jeffrey, I think. So this result is independent, but it agrees. And the rule is as follows. So basically what you do is to promote Bayes inverse to a fully fledged channel. So now this is not just a conditional probability on the hypothesis given a specific value of the observed data, but now this is a noisy channel that back propagates your new data, sigma I, back onto the hypothesis. So basically you channelify, you make Bayes inverse a channel, and then you use this channel to bring back new data on the hypothesis. And of course, the usual Bayes rule is recovered when this sigma I is just a delta distribution. Okay. So now these derivations are nice, and they are very famous, in fact, but they have a problem. And the problem is that they rely on a set of axioms, which may appear compelling to some, but necessarily not so to everybody else. Okay, when you have a set of axioms, you have a nice axiomatic formalization of your theory, but axioms may not look compelling to everyone. So what is an alternative approach? An alternative approach to axioms is to start from a concrete task, is to start from some variational problem and try to look for the solution to this problem. So the question could be formulated as follows. So can Bayes' rule be derived as the optimal unique solution to a concrete task? And surprisingly, looking at the literature, at least from the side of quantum information theory, this was not clear. Typically, Bayes' rule provides some kind of pretty good approximation to the optimal solution, right? So we had to look in the literature to find an actual problem where Bayes' rule is the solution. So what is this problem? This problem is based on the idea of minimum change update. Okay, so the idea is that you start from some belief about an event, for example. Then you are provided some evidence about, for example, like a random variable that is correlated with the hypothesis. And now you have to change your belief in such a way that the new belief is consistent with the data. So you want to accept the data into your belief system. So let's read it together. So to avoid unwarranted bias and remain maximally non-committal, the updated belief should be consistent with the new information, which is the result of the observation, possibly a noisy observation, while deviating as little as possible from the initial belief. So how can we mathematically formalize this idea? So this is how people do typically in classical probability theory. So again, we are given a channel, a discrete noise channel, finite channel, the simplest case, mathematically speaking, a pi given x and a prior on the input gamma x. And from these two ingredients, we construct the forward process, which I denote with this star product here. Okay, so you start from your channel P, from the prior gamma, and now by taking the product of these two, you get a joint probability distribution on the input and the output simultaneously. Now I give you new information on the output, so some probability distribution sigma of I, and consider the following problem. So here you have some suitable information divergence, D, and you compute the divergence between the forward process and something else, okay, that is constructed starting from the distribution on the output sigma and some channel R, which is a channel that goes the other way. So a channel that starts from the output and give you an input. So this is a reverse channel, okay? So basically what you want to do, you want to find a reverse channel R that minimizes this statistical divergence between the forward process and the joint reverse process. So you see that all the constraints here are met because the forward process starts with your prior and with a given channel, whereas the reverse process begins with the new information. So it is consistent with the new information by construction. What you can minimize is this reverse channel R. Now, as it turns out in classical probability theory, for many reasonable choices of this divergence, D, for example, this could be the Kalbach-Lieber divergence, it turns out that the arg min of this problem is uniquely given by Bayes inverse. Okay, so in order to formulate the quantum analog, the fully quantum analog of Bayes' rule, we said, why not begin instead from a quantum version of the minimum change principle? But there is a little problem in quantum theory. The problem is that in the classical case, the minimum change principle is formulated using the joint input-output distributions. Okay, and what you want to minimize is the divergence between two input-output objects, one that corresponds to the forward process and another that corresponds to the reverse process. So you don't start just, you don't use only their marginals. You really want to use the process, the input-output process. But in quantum theory, this is a problem because we know that there is no quantum description of an input-output process. Okay, so well, there are proposals. I also worked on these proposals. Sometimes they're called like state over times. The problem with these objects is that they're typically not positive. And so it is difficult to put them into divergences because divergences work well with states and work much less well with things that are not state. Actually, I'm not sure how they work if the operators are not positive semi-definite. So we had to use something that is less exotic than a state over time, but still has the flavor of an input-output joint state. And this object is something that is derived from the Choi operator corresponding to a channel. So I give you a channel, that is to say, a completely positive trace preserving map from some input system A to some output system B. And given the channel E, you define the corresponding Choi operator that in finite dimension is simply defined in this way. Okay. Then from the Choi operator, a possible way to define something that gives you back the joint input-output probability distribution in the classical case is the following. You take the Choi operator and then you sandwich it on the left and on the right by the square root of some state gamma that plays actually the square root of the transpose of a state gamma that corresponds to your prior quantum belief. So when you have this operator, it is very simple to verify that it is not actually an input-output state, but almost, because if you take the partial trace over the input, you get, in fact, the output, okay? So you get E of gamma. And if you take the partial trace instead over the output, you get something that is not quite the prior, but it is the prior only up to a transposition. So you get as close as possible in a sense. And of course, when all these operators are diagonal, that happens when all things commute, right? So you can say that this is the classical limit of this setup. Of course, you get back to the classical joint input-output probability that I showed you before, right? Because when the operator is diagonal, taking the transposition doesn't do anything at all. So you can say that this is a possible generalization of this input-output forward process with the benefit of giving you a well-defined bipartite state. This E star gamma, this object here, is a bipartite quantum state. And so it can be plugged into a divergence without any trouble. So now then, we are ready to formulate a quantum version of the minimum change principle. It reads as follows. So given a channel E, a prior state gamma on the input system, and some new information sigma B. Okay, so these are now density matrices. We consider the problem of minimizing this statistical divergence between this Choi, let's say Choi joint state, this quantum forward process, and a quantum reverse process that takes this new information and back propagates it onto A by means of a CPTP map R. And then you take the minimum over R. You need a transpose here because you want to compare, this is a state on BA, and you want this to be also a state on BA. And when you take partial traces, you want the transpose to appear on the same system, right? So if you do things carefully, you see that you want to put a transpose here. And this is what we obtained. So we weren't able to deal with the Umegaki quantum relative entropy here for technical reasons. But we were able to deal with another divergence, which is very well defined and something that we all know and love, which is the Ullmann fidelity, the quantum fidelity, the trace norm of the square root, the product of the square root of two density matrices. Because I recall you, these two objects are both well-defined bipartite density matrices. There is another technical caveat in the theorem that we have. Oh, here, sorry, I didn't update the reference. It's been published last August, so roughly 1 month ago on Physical Review Letters, that this object need to be invertible. Okay, this is a technical limitation for the theorem as it is. I don't find it too annoying in the sense that if you are into a Bayesian mindset, so to say, you don't want to assign probability 0 to anything. Like to assign probability 0 to something is an extremely, extremely, extremely strong assumption. You know, you are basically saying that that event will never occur ever. Okay, so you can say if you have objects that are not invertible, okay, just add an epsilon amount of something that is invertible. That wouldn't change much your belief, and still this would make this theorem true, okay, applicable. So what happens? So if you maximize now, because the fidelity, okay, you want to maximize the fidelity, right, in order to minimize the divergence. If you maximize the fidelity between these objects, you get this channel here. This is unique, okay? You see this argmax returns a singleton, okay? So this solution is optimal and unique. And this channel depends on everything. Depends on the forward channel E, depends on the prior gamma, and depends on the new information sigma, and is given explicitly by this formula. So you see that you have slightly complicated things here. You have these sandwiches with fidelity, with square root operators that are probably signature of the fact that we start from the fidelity as the figure of merit. But then the structure is very similar to something that many people, I think, would recognize as the Petz map. We will come back on this point later on. So first of all, in general, when E of gamma and the new information do not commute, the dependence of the posterior on the new information is not linear. You see, because sigma appears here as well. If E gamma and sigma commute, of course, you can bring this here, and then you can simplify this with this, because it is invertible. So basically, sigma disappears from the formula of the channel. But in general, if these two operators do not commute, you still have some square root of sigma here. So the dependence is not linear. Is this a bug or a feature? I don't know. We don't know. We leave it up for future research. And then another question, of course, is what happens when other divergences are used instead of the fidelity. For example, Umegaki quantum relative entropy, or Holevo fidelity, for example. And then also, what about multipartite situations? Or, for example, when you have locality restrictions and so on. So actually, we consider this problem, of having some kinds of, here, you just have two systems, A and B, without any further structure, but you could say, okay, I start from a bipartite system, and then the channel acts only upon half of it, for example. Okay, so this is a problem that we consider with Nagasawa-san in the other paper, but I don't think I will have the time to go through it in detail. So just to say that this is we consider this to be the beginning of a new research inquiry that I think it's quite exciting, because, Bayes' rule is so central to so many different areas of science, from statistical mechanics to machine learning, for example. And here we have formulated the first fully quantum version of it. And so we expect it to have at least as many applications as its classical counterpart. As an example of one application, I would just to quickly mention how you can apply this quantum Bayes rule to the problem of quantum state inference prediction from measurements outcomes. And this is related with macroscopic entropy. The motivation comes from the other von Neumann entropy. So we usually know, von Neumann entropy, which is a minus trace of rho log rho. But in his book, von Neumann, after introducing this, says, but pay attention, because in thermodynamics, this is not what you want to use. You want instead to use this thing instead, which is what he calls macroscopic entropy, which is formulated as follows. So for a density matrix rho and a positive operator valued measure for POVM P, the macroscopic entropy of rho with respect to POVM P is given by this, where PI are the probability of outcome, and VI are what are called volume term. This is something that interpolates between, you see, some kind of a Shannon entropy of the outcome. And so if you only look at this part, PI log PI, whereas if you only look at this bottom part, log VI, you see that it is something that looks like Boltzmann entropy. And then you have the ratio of this thing. So actually, this is a relative entropy. Actually, I would think, we call relative entropy like the Kabla-Kleber divergence, but I think that already in this definition by von Neumann, there is a notion of relative entropy. This is in fact a relative entropy, even though, of course, von Neumann doesn't call it so, but it's an average of a log of a ratio of numbers. Anyway, this is a different story. So what is the meaning of this? So the meaning of this object is immediately recognized if you see the trivial fact that macroscopic entropy is just the relative entropy between the probability distribution of the outcomes when you measure on rho and the outcomes when you measure on the uniform state, the maximally mixed state, apart from some normalizing constant here. P here is this quantum classical channel, okay, that gives you from a state, it gives you the classical probability distribution of the outcomes when you measure P of EMP. And it is very simple to prove the following theorem, that the difference between macroscopic entropy of rho and its von Neumann entropy, so which is called microscopic entropy, we can call it this observational deficit. We call it so in the paper with Nagasawa-san. Okay, so it's a gap between macroscopic entropy and von Neumann entropy, is upper and lower bounded by things that depend on somehow the difference between the microscopic state, let's say the true state of the system rho, and something else, this rho tilde p, which is given by this. This rho tilde p is something that can be reconstructed only from the knowledge of the measurement done, the P of EM element pi, and the probability outcome, the statistics of the outcomes. Okay, so this rho tilde p is something that can be reconstructed only knowing which measurement is made and which are the outcome that are obtained. So somehow the difference between macroscopic entropy and von Neumann entropy tells you something about the difference between the true state and the state rho tilde p. So the question now is to say, what is the meaning of this rho tilde p? So rho tilde p is nothing but what you obtain if you apply on the classical distribution that you obtain from rho by measurement P of MP, the Petz recovery map constructed for this QC channel P and the maximally mixed state U. So Petz transpose map or Petz recovery map, Petz recovery channel, it goes under many names, but it's a cornerstone of quantum information theory, I would say, because it captures the idea of statistical sufficiency in quantum statistics, and is defined as follows. Okay, so a Petz recovery map for a channel E and prior gamma is given by this. So you have a sandwich with the inverse of the square root of E of gamma. You put your input state here, right? Then you back propagate using the Heisenberg picture, the trace dual of the channel, and then you sandwich with the square roots of the prior. And Petz recovery map has been first discovered by Petz in the 80s, but then it's been rediscovered independently many times, just because it seems to be a very natural concept. It's been rediscovered by Barnum and Neal, that they call pretty good quantum error correction. They were not aware of Petz result at the time. It was, I think, early 2000. And then it's been rediscovered roughly at the same time by Crookes, when he tries to construct a quantum reverse channel. And later it's been applied also in quantum gravity. There are results by Pennington and others where they use Petz recovery map to do this entanglement wedge reconstruction. So it seems to be something very central, and it is kind of mysterious why it keeps popping up in so many apparently unrelated areas of theoretical physics. But I think that in this talk, I will provide you with the possible answers to this pervasiveness of Petz transpose map, because you can immediately recognize, so the question is, what is the meaning of Petz transpose map? Petz transpose map is, well, it coincides with our quantum Bayes inverse, quantum Bayes rule, whenever sigma and E of gamma commute. So in particular, for a QC channel, you see, a QC channel has a classical output. It means that the output is supported by an abelian algebra, so operators there commute, and so by construction, you know, any new information will commute with this output if you have a quantum classical channel, you know, a POVM measurement, for example. And therefore, in the case of a QC channel, which is the case that is relevant for macroscopic entropy, Petz transpose map is exactly the quantum Bayes rule that we obtained. Okay, so it has a very strong motivation why Petz transpose map plays a role there. It's just Bayes rule at work in the problem of quantum state inference from classical outcomes. And so since, let me read it here, since the measurement channel P is quantum to classical, this rho tilde P that appears in the definition of macroscopic entropy is the unique retrodicted state that satisfies the minimum change principle. And therefore, the entropy difference that we call the observational deficit, okay, the difference between macroscopic entropy of rho with respect to measurement P and Phenomenon entropy, measures somehow the amount of irretrodictable information. So it tells you how much more noisy, how much more uncertain these observed values are with respect to the true unobservable state rho. Okay, and now, if you want, but I don't think I will have time to do this, because I should conclude my talk, you can actually say, you can introduce the set of macroscopic state now in a very logically cogent way, because now you're just using Bayes' rule, or, well, it's quantum version, right? So you can say, what does it mean for a state to be macroscopic? A state is macroscopic whenever the observational deficit is 0, okay? So that is to say, when rho is equal to rho tilde. Okay? And then what it means that because we know that rho tilde is obtained from P just by acting on it with this Petz transpose map, the problem of characterizing macroscopic states basically boils down to the problem of characterizing the set of fixed points for this channel. Okay, so this set of fixed points depends on the P of EMP and the prior gamma. And then there is a wealth of results in operator algebra and quantum information theory that helps you actually work out an explicit characterization for these objects. And this is what we were able to give together with Nagasawa-san. This is the result. So you have to find out some post-processing of the given POVM. So this is a conditional probability distribution. So you are post-processing this POVM into a projection valued measure. This is a PVM, all right? And then this PVM also has to commute with the prior. And once you have this object, you can construct macroscopic states in this way. Okay, so this is an if and only if, and so you have an explicit characterization of macroscopic states. And then from these states, you can actually work out a resource theory. But I realize that I don't have time to go into that. You can actually say, so what are now the transformations that preserve macroscopic states? And so you see that you are heading into a resource theoretic sort of language. We have results about that. We have results that characterizes channels that do not, create microscopicity. Okay, so channels that are macroscopic. And you can go on, but I will skip to the conclusions. I'm sorry, I think I talked too much. There is also an H theorem for this. There is a nice connection with this famous Japanese theoretical physicist, Satoshi Watanabe, who was the first to, this is from an abstract of a paper of his, where he is strongly pushing to abandoning the confusing wording of irreversibility in favor of irretrodictability. So irreversibility, because it seems that the process is irreversible. It's not. The process are always reversible. You know, basic equations are always reversibles. What are not reversibles are our inferences on the processes. And I think that this line of research that we developed in the past few years actually make Satoshi Watanabe claim extremely clear and extremely solid, extremely compelling. So conclusions, take-home messages. So we have derived the quantum analog of Bayes' rule based on the principle of minimum change or a generalization thereof. The quantum Bayes rule coincides with patch transpose map for channels with commutative output. And this gives an operational meaning to the retrodicted quantum state inferred from a measurement's outcome. Now, the difference between observational entropy and phenomenon entropy, which we called observational deficit, quantifies the amount of irretrodictable information. And the second law, but I didn't talk about this, can be seen as a statement about the generic loss of retrodictability. So it has nothing to do with reversibility of irreversibility. What it tells you about is retrodictability and irretrodictability. And I thank you very much for your attention. Are you still there?
Hayashi Sensei.
So there is no one from China.
One from China. Oh.
Maybe they went for lunch.
Yeah, but そんなことないと。
Sorry,
Okay,
hello.
so if,
Can you hear me?
yes, of course.
So Mike does not work. So thank you for nice talk. So any question? What? Sorry, could you show me the your main result?
Okay. Well, there are many main results, but the main results of this talk is this. Is there anything particular you would like to hear about? Hello? What's happening?
In China, some problem happens on the sound, I think.
Oh, I see. Maybe it was not a good idea to use Zoom.
Mm-hmm. Maybe
Oh.
you can use chat box and write some comments.
Some comments of what? Me? I don't know what to comment about.
Hayashi sensei, if you have some comments, can
あ、
you?
書いてください。林先生。チャット使って書いてください。はい。
Can you hear me?
はい、聞こえてます。
I could not understand the meaning of that fidelity.
Okay, so maybe I should start again from the meaning of these two operators, right?
Yeah.
So what are these two operators? So the first operator is let's say it's a quantum version of a forward process. So a process is not just a channel in this talk. A process is a joint input-output distribution. So how do you do it in the quantum case? So given a channel, which is a CPTP map, you first construct the Choi operator, okay? And then you construct the forward process by taking the sandwich here with the square root of the transpose of your prior state gamma. Okay, so gamma is a prior, E is the channel, and from these two objects you construct a bipartite state. 二重状態. You construct a bipartite state. You would need the transpose here because this is the Choi operator. And so we know that you need a partial transpose in such a way that if you take the partial trace on the input, you get the prior, I mean, the output corresponding to the prior, okay? Whereas if you take the partial trace over the output, you get the prior with a transpose, okay? So now, what is this object here? So this is the forward process, prior and channel, and this is the thing that you want to minimize, but with a constraint. The constraint is that the sigma is the new information that I give you, okay? Because Bayes' rule has also this piece, you know? It has a prior, it has a likelihood, but it also has this new information, okay? Which is given most generally as a probability distribution in the classical case. So here we have this new information, which is given as a quantum state on the output, sigma b. And now, by following exactly like literally by following the formulation of the minimum change principle in the classical case, you minimize this divergence over all CPTP maps, so over all quantum channels that go back from B to A. You see, so you are choosing a reverse channel that minimizes the divergence between the forward process and this, you know, this new information. Okay, so you are not interested only about the marginals. You are really interested about the input-output joint state, and you want to minimize the divergence between these two objects: the forward process, which is given, and the reverse process that is optimized over the channel R. So now what we have done is to use as divergence the quantum fidelity, because we were able to do calculations in the case of quantum fidelity. Of course, the fidelity you want now to maximize, right? Because the fidelity is not a divergence, but it's a minus divergence, right? So you want to maximize the fidelity between the forward process and the reverse process. And what you find is that the solution is unique, okay? And it is given by this map. This is a CPTP channel, okay? That depends on E, on gamma, as it should be, right? Because it is a Bayes rule. But now it also depends on sigma. And this is somehow the puzzling feature of this thing, because typically sigma should not be here, right? For example, suppose that if E of gamma and sigma, if they commute, okay, then you can bring sigma here and then simplify, right? So sigma would disappear and you would get a Petz recovery map. So this is not quite a Petz recovery map, but it coincides with the Petz recovery map in all situations where E and gamma and sigma commute. So implicitly, we also gave an operational task in which Petz recovery map is the optimal solution, is not a pretty good approximation of the optimal solution. You know very well that Petz recovery map is, is basically always pretty good, pretty good measurements are a kind of Petz recovery map, pretty good error correction, but it's never optimal for anything, okay? So here there is an operational task in which Petz recovery map is optimal.
So sorry, still I cannot understand. Why you need to consider that time reversal one?
Because now what I give you here is a state on the output, sigma, right? So now you need a channel to have, at the end you want a joint state on A and B. So on input and the output. This is a joint state on A and B together. What I give you as new information is a state on B, on the output, okay? And so you need a channel to bring it back to the input so that this object here is also a joint bipartite state on A and B at the same time. And if you look at the classical Bayes rule, this is what it gives you, because classical Bayes rule essentially, classical Bayes rule starts from a channel. Forget this I/O, okay? So this is a noisy channel from input to output. You have a prior on the input, and classical Bayes rule gives you a channel from output to input. So in the same way, you want here to find the best recovery channel, in a sense, the best channel that minimizes this divergence, so that achieves this minimum change. Where change, again, this is important, change is not something about the marginal distributions, but change is something about the whole input-output process. This is the crucial thing.
Okay, thank you very much.
Thank you.
So this next speaker is Jinpei Zhao, but
Hello, can you hear me?
Yes, from Nagoya you can, we can hear your voice. And the slide is okay?
It's so easy. So good afternoon, everyone. I'm Jake Zhao from the Department of Information Engineering of Chinese University of Hong. I speak today. The title is Search for an Analog of the Sub-Additive Doubling Rotation Proof for Gaussian Optimality in Quantum Systems. So the talk will consist of two parts. The first part, I want to introduce the general idea of this sub-additive doubling rotation proof idea, and then demonstrate to you the application of this proof technique on a very important result called the entropy power inequality. And because I'm very new to this quantum area, so I will be spending most of the time on the first part. And in the second part, I will briefly discuss about the possibility of expansion of this idea to the quantum system. So let's begin with some basic notations. The first one is Shannon entropy, which is defined by the summation of P log P. And differential entropy is the analog for Shannon entropy in the continuous variable case. The mutual information is defined for two random variables. You can consider it to be some metric to measure the correlation between two random variables. For example, if you take x to be equal to y, then the mutual information is the entropy itself. And if you take x and y to be independent random variables, then the mutual information is 0. And the definition for conditional mutual information is similar to this. We just replace every distribution function with the conditional distribution function, and then take the average of the random variable over the random variable z, then we get the conditional mutual information. Okay, and here's a definition for Markov chain. So we say three random variables, x to y to z, forms a Markov chain if we consider about the conditional distribution pz given x and y is equal to pz given y. So this is saying that if you're given fixed value of x and y, then the distribution of z depends only on the value of y, but not depending on the value of x. And the equivalent condition for this Markov chain is that the conditional mutual information between x and z given y is 0. And the last one is the Gaussian distribution. So we're considering about the n-dimensional random vector. So suppose we are given the first and second moments, mu and k, then the density function is given by this formula. And we can actually calculate that differential entropy of this Gaussian random variable is given by half log 2 pi e to the power n determinant of k. So as expected, this formula is independent of the mean of this random variable. So let me now introduce the general idea of this sub-additive doubling rotation proof technique. So we first let f to be some functional defined on the probability distributions, and as in the information context, we have this shorthand notation for this functional. We write fx instead of f of the probability distribution of x for convenience. And we assume those three properties for this functional. The first one is called the strict subadditivity. So in the information theory context, we say a function is subadditive if f of x1 and x2 is smaller than f of x1 plus f of x2. And we call it strict because there's an extra condition for the equality condition. So it is if and only if x1 and x2 are independent, then the inequality holds. And the second property is called the rotation invariant. So suppose we are given a random vector x, and we put a unitary transformation on that that vector x, then the function value remains the same. So in the later proof, we'll denote this x plus to be x1 plus x2 over square root 2, and x minus to be x1 minus x2 over square root 2. And this will suffice for the proof. So we just consider this unitary transformation only. And the third assumption on f is that f is continuous in the distribution space. So this is for some analysis of purpose. So our goal here is to maximize this functional fx subject to bounded covariance, where this f satisfies the above three properties. So now we suppose that px star is the maximizer. So here one may ask that does this maximizer really exist? So if we look at the set that all of the distribution with bounded covariance, it is actually in general not a compact space, but we have assumed that f is continuous and can deal with this problem and prove that this maximizer actually exists. So then we denote the corresponding maximum value by the v, and then take two independent copies of this maximizer, x star, say the copies are the x1 and x2. Then we can have the following observation. We write 2v to be fx1 plus fx2. This is by construction of x1 and x2. And then this is equal to fx1 and x2. This is because of the strict subadditivity property. And the third step is we rotate this vector. This is by the second property, so this equality holds. And then again by the subadditivity, this is smaller than fx plus fx minus. And because we assume that the b is the maximum value, then by this assumption, this addition must be smaller than 2b. So by this observation, we conclude that all of the inequality in this derivation must have been equality. So therefore, we conclude that x plus is independent of x minus. This is also because of the strict subadditivity property. Before the goal of the proof is that we want to prove that the maximizer is Gaussian distributed. So this comes from a very important theorem called the Kat-Bernstein theorem. So let's see. So if x1 and x2 are independent, and further we have x1 plus x2 is independent of x1 minus x2, then they must be Gaussian distributed with the same covariance. And here I wrote down the proof sketch for the one-dimensional case, and it is easier. It is very easy to generate, extend this proof to n-dimensional. Suppose the characteristic function is defined to be the expectation of exponential itx. Then we can write the characteristic function of this random variable pair. In two ways. First way is in this way, and the second way is in this way. So it's basically by those two independent conditions. Then we equate these two ways of writing, and we get the equation, and we try to solve this equation, and we will get that the characteristic functions must be in the form of these exponential functions, and this will prove this theorem. Here is some background of this proof. So the original proof, the original use of this proof can be back to early 90s by some works in functional analysis by Carlin and Leeds, etc. And then in 2012, it was discovered in the context of information theory by Gan and Nair, and this was used for proving the capacity region for Gaussian broadcast channel with private and common.
Excuse me, from Nagoya, we cannot hear your voice.
Some internet issue.
I see. Okay.
You see now?
Yes, it's okay.
So,
Please go on.
Thank you. So let's consider x1 and x2 to be independent copies of maximizer x star, and again let the b to be the maximum value. Then we write the 2b in this form, which is entropy of x1 and entropy of x2. And by properties, we can get this is equal to h of x plus and h x minus, and then we use separate the terms out, and we find that h x plus and h x minus by optimality it's smaller than 2b, and it must hold that the gap, which is the neutral information between x plus and x minus, must be 0. And hence, we can use the Keck-Bernstein theorem to conclude that x plus and x minus are independent. So, very interesting. Before I try to introduce you the proof of EPI, I first introduce what is EPI. So Shannon in 1948, in this very famous paper, proposed the following inequality, which is called the entropy power inequality. So if we take two independent continuous random variables, x and y, and dimension d, and we further assume that the second one is bounded, so the differential entropies are well defined, then we have the following inequality to be true. And the equality condition for this inequality is that x and y are Gaussian distributed with proportional covariance matrices. So a very big step towards proving this EPI was Leib's equivalent form. So in this form, Leib's proved that the EPI is actually equivalent to saying that if we are taking infimum of this functional over x independent of y, and if we can prove this functional is bigger than 0, then it's equivalent to prove the EPI. So this form is better because we can get rid of the exponential terms, so it can be easier. So the first proof was by Stam in 1958. He proved this EPI on the work of the Grun's identity that constructs certain links between the differential entropy and another quantity of future information, and then use some inequalities in efficient information to show that this inequality holds. And in later years, several proofs of this inequality has been discovered, but almost all of them follow a very similar approach, which is you find some relationship between the this inequality and Fisher information, and use the results in Fisher information inequalities to prove the EPI. But this proof I'm going to introduce, which is called the sub-additive double interpretation proof, is I think it's a very new approach because it didn't use any Fisher information inequalities. So instead of showing this API directly, we show a more general form, which is called the conditional API. So suppose X and Y are so the only difference here is that we assume X and Y is independent given U, and then we can replace every term by the random variable given U. And you can see that this theorem is actually stronger than the original EPI, because if we take U to be constant, then it reduces to the original EPI. And also there's a Lisp form for this. So there's a very important proof element of which is called double Markovity. So this is proved by Auschwitz and Kerner in 1974. So the theorem is follows. So suppose you have A to B to C and A to C to B. And then there exist some functions, G and H, which is one is on B and one is on C, and they are equal with probability 1. And given this function, there's a typo to this G of. So given this G of B, A and B, they are conditional. So in a very special case where we suppose BC has full support, then we can write the formula in this way. So we show that FA given BC is actually FA itself. So this proves that A is independent of BC. It's very one-line. So we can start the proof now because of the Leibniz equivalent rule. So we can sufficiently just prove this inequality. But in order to use the double Markovity and to assist some analysis, we add some perturbation to the original function, which is first one is the additional mutual information term, as you can see at the end. And another thing is that we perturb the random variable a little bit by adding the Gaussian noise. So this allows us to work on random variables with full support because we are adding a Gaussian noise in it. And later, if we can prove that the G is maximized by Gaussian, then we can just take the sequence of functions with this epsilon and delta goes to 0, then we can argue that the limit also is maximized by Gaussian. So here is a very long calculation.
Hello, can you hear me? So previously you mentioned that using the Fisher information form, but you didn't explain Fisher information until now.
No, because I think in this kind of proof, we don't actually need to use the Fisher.
When you use the Fisher?
Well, I just want to argue that in the original proof by Stan, the API was proved by using this.
Original proof, another proof. Okay.
In the later several proofs, we also use. But this proof is a little bit special because it doesn't exist. So we are here. So let's begin with the calculation. So suppose we are taking again we are taking independent copies of x star y star, which is x1 y1 and x2 y2, be all independent given the random variable u. Then again we just write 2b in this way and rotate it. And then we use the chain rule and Markov structures to write the formula in this way, in this very long term. And we observe that the red part is actually g x plus y plus given u, and the blue part is g of x minus y minus giving u star and x plus y plus. So these are two potential maximizers. So they must be minimizer in this case. So they must be bigger than 2v, and the rest of the terms are the gap of the inequality. So again, we can conclude from this derivation that all of the gaps of the three terms, they must all be zero, because the mutual information must be positive. And it turns out that we only need to use the fact that the second term is zero. So from this term to be zero, we can conclude that firstly, this blue term to this red term to this purple term is zero. And the second equality is from some obvious observation, which is the red term to the blue term to the purple term, also a Markov chain. So now we can use the double Markovity theorem to conclude that the blue term and the red term together, given u, is independent of this purple term. And then in particular, we have this blue term is independent of this purple term. And then because we are just adding the independent Gaussian to this x minus and y minus, then we can conclude that actually this blue term is independent of x minus and y minus, and which is the thing that we want. And then by the Bernstein theorem, we prove that x1 and x2 are Gaussian. So let's finish the proof. Okay. Then the second part is potential to quantum system. Again, these are some basic notations, but I think I don't have time, so I just jump over it. Here is the quantum system entropy inequalities, which is proved by Koenig and Slate in 2012. They show that given rho x and rho y to be 2 n-mode states, then the quantum API can be formulated in the following theorem. So this E lambda is a mapping associated with the beam splitter of transmissivity lambda. And here we get the quantum API and also the Leipzig equivalent form. The authors, they actually formulated a bunch of analogs of like random variable addition and additive Gaussian noise and also coefficient information. And after formulating this, they proved the Brunn's identity and Stam's inequality for quantum settings. And then basically, based on the Stam's idea, they make the proof to go through. And in particular, we're interested in the quantum analog for the addition, which is in this way. So in classical, it's just x plus y, which we note that x and y are independent here. And the author argued that we can use this beam split system to mimic the addition in our quantum system. So which is, we first take rho x finite per rho y, and then multiply by some unitary transformation, and then trace out the system y. And this is the definition of this Gaussian unitary U lambda. So these constructions have the following properties. The first one is that the output of this mapping has covariance matrix lambda. It's a combination of gamma x and gamma y, which are the covariance matrix of x and y. And so if you have gamma x and gamma y to be the same, then this will leave the covariance matrix invariant. And the second observation is that if we write the characteristic functions, we actually get, so this is before tracing out the y, so the characteristic function of this thing can be written as the multiplication of a characteristic function on x and a characteristic function on y. So this inspires us to give an analog for the Cac-Bernstein theorem. So if we define just like x plus and x minus, we are defining rho plus to be this tracing out the y and this tracing out the x. Then by the previous observation of characteristic functions, we can again write the characteristic function of this thing in two ways, which is two terms of multiplication and also both of multiplication. And then the remaining proof is kind of identical to the classical proof. This is on the characteristic function space. So I want to say that this can be readily to apply on the theorem that Gaussian state with this fixed covariance gamma is actually the maximizer of all of the states with this fixed covariance gamma. So the proof is exactly the same as case. So the goal of our research is actually developing this tool of proving things in classical case to the quantum case. So one example is the double Markovity. So if we have those four random variables, and for simplicity, just prove it with full support, and we have those two Markov chains. Then in the classical case, then we from this and this we implies that x, y are independent of z. But one question to ask is there a quantum equivalent to this result? We're still working on it. So here is the summary and some future work. So the first one is that the sub-additive doubling rotation techniques gives alternative proof of Gaussian optimality in various of problem settings. And sometimes if the traditional perturbation-based techniques doesn't work, and this technique might work on that situation. And the second thing is that the extension from the classical case to quantum cases actually becomes more challenging if you have the conditional entropy terms and as well as some complicated Markov structures, and then it becomes more and more complicated classical. And so our current research is to develop some extension of this tool to the quantum case. I think that's all for my talk. Thank you very much for your time.
Thank you very much. I'm slightly confused your talk, but firstly, in my understanding, quantum entropy is fully proved by
Yes.
Behe and other guys.
Yes. You mean the entropy power inequality?
Yes.
Yes,
So
yes,
this version is slightly different. I'm slightly confused.
You mean this one?
Yes.
Case from
Good. Kennedy, but
it's related by
but this version is not so strong. So recently, Harman Beigi and Hami Harvey showed a slightly different version. This one is a much more generic one. Maybe this version is slightly weaker than.
Yeah, yes, we actually know that version that was presented maybe last year, I think, and that one's more general and more strong. But I picked this because this is shorter, easier to show.
So I'm quite confused. So your method doesn't work for that general case for the Beig's statement. So you can only show that's all the parts by using your method.
Well, I still cannot show this by our methods. It's an ongoing research.
Ongoing.
So,
Even
we are
with
just
this,
at the beginning part.
even with this version.
Yeah, even with this version, we cannot show. It's just an ongoing research. Yeah, thank you.
Sorry, any comment from Nagoya side?
Yes, one from Nagoya.
Thank you for the talk. So in the case of finite quantum systems, then there is a structure theorem for quantum Markov chain, which have a direct sum decomposition of B into some subspaces, and we have a separability between A and C, etc. Is there any similar analog for continuous variable quantum systems?
Okay, actually, I don't know. I just started this research recently, so
Okay.
not sure about this.
Okay, so if you can kind of extend the finite dimensional result to continuous variable systems, or maybe someone already did, but it will be, useful.
Okay, thank you for the suggestion.
I'm slightly confused. This one considering M mode quantum state. This means that the continuous system, I think, not discrete. This talk considering the continuous case, even in the quantum case.
Yeah, I think so.
Is there any question or comment?
Sorry.
Okay, so now almost time finished. So thank you very much. Then we want to proceed to the next speaker. Next speaker is Chui Wang from Edinburgh. So could you start?
Hello, everyone. Thank you for the introduction. My topic is bridging quantum query and sample complexities, theory and applications. And I'm Qishen Wang from the University of Edinburgh. And so this question is about quantum query complexity and quantum sample complexity. And as you can see, query is colored and sample is colored. And the title here is shortened as quantum queries, a bidirectional bridge with quantum samples. So, and this talk is based on several works, a combination. So, first of all, quantum query complexity is a well-known complexity in quantum computing. Given a unitary oracle U, the quantum query complexity measures how many queries to controlled U and controlled U dagger are needed to test a certain property of U. As shown here, U1 to UQ are queries to U, and Q is the number of queries, and we call it query complexity. An example is quantum search, and given oracles U that maps I0 to Xi, and the goal is to determine whether there is an index I star such that Xi star equals 1. And it is well known that the query complexity of this problem is theta square root n. Another example is the quantum amplitude estimation. That is given oracle U, which maps 0 to square root p 0 plus square root 1 minus p 1. A decision version can be to determine whether p is less than half minus epsilon or p greater than half plus epsilon. And the query complexity is known to be 1 over epsilon. And about sample complexity, in the quantum computing, given an unknown quantum state rho, the quantum sample complexity measures how many copies of rho are needed to test a certain property of rho. As shown in this circuit, we have S copies of rho to do some performance W unitary quantum circuit and do some measurement. And then we know some properties from rho, and here S is the sample complexity. An example is the quantum mixedness testing that is given a d-dimensional unknown quantum state rho, and the goal is to determine whether rho is maximally mixed or rho is epsilon far from being maximally mixed. And the sample complexity is theta d over epsilon square. So our motivation and our question is there any relationship between quantum query complexity and quantum sample complexity? And these two quantum complexities were studied separately in the previous literature. So let's go into our first part, quantum sample to query lifting. For a property of quantum state P, P yes and P no, we define the quantum sample complexity SP. That is how many samples of rho are needed to determine whether rho is in the yes set or rho is in the no set. Given the promise that it is in either case. And also, we can define quantum query complexity, a kind of quantum query complexity, and we denoted Q diamond P here. That is how many queries to U rho are needed to determine whether rho is yes or rho is no. Here, U rho is a unitary operator such that its upper left corner is rho over 2. And here over 2 is a technical issue. And we can show that the query complexity here can be related to the sample complexity S. That's Q diamond P is greater than 2 omega square root SP. This means that there is always a query lower bound being the square root of the sample lower bound. As an application, we can use this relationship to show quantum carry lower bound for quantum Gibbs sampling. So for this problem, given a unitary oracle U that is encodes the information of H, Hamiltonian H, in the upper left corner of U, and the goal is to approximately prepare the Gibbs state e to the minus beta H with normalization factors for beta, for asymptotically large beta. The upper bound is known to be O beta, and this is due to the result of Guillen, Su, Low, and Webb. And we can show a lower bound here by the quantum sample to query lifting, which is almost tight. And our goal is to consider the problem P beta, which distinguish the two states. P plus minus is the half minus plus beta over 2, and here is half plus minus beta over 2. Formally, P beta is defined by the property P beta yes and P beta no, and P beta yes contains only one state P plus, and P beta no contains only one state P minus. And we can show that this problem has sample lower bound beta square. Okay, and then the Gibbs state of the Hamiltonian half rho plus minus. After some calculations, we can show that the Gibbs state is proportional to e to the plus minus 1 and e to the minus plus 1. And this state can be distinguished with O1 samples. That means if we can prepare a quantum Gibbs state with query complexity Q, this problem can be used to distinguish rho plus and rho minus, and that's why the query complexity Q is greater than or equal to Q diamond P beta. And then by the lifting, we have Q diamond is greater than or equal to square root SP beta. And SP beta here is beta square, and this is, by calculation, it's till the omega beta, which is almost tight. And there are other approaches to proving the query lower bounds for Gibbs sampling by other approaches. And here we also present a second application, the entanglement entropy problem. And the problem is, given a unitary oracle U that is a reflection operator about kit psi, and psi is a bipartite state of d dimension. Each part is d-dimensional. And the goal is to determine whether the 2-Lenny entropy of psi is less than or equal to A or greater than or equal to B. And we denote delta to be the difference of B and A. And we can show a lower bound for this problem, that is tilde omega square root d over delta. And this improves the previous lower bounds, omega d to the 1/4 and 1 over square root delta. And the proof sketch is also simple. We consider the problem P of determining whether a mixed state rho has entropy less than or equal to A or greater than or equal to B. And this problem is known to have sample lower bound d over delta. And let purified P be P where copies of purification of rho are given. And because this is a unitarily invariant property, we can show that the sample complexity of the purified version of P is equal to the sample complexity of P, which is omega d over delta. And then note that the reflection operator and U prime, whose upper left corner is k psi bra psi over 2, can simulate each other with Owen queries. And we finally can show a lower bound for this problem. That's any problem with query complexity Q can determine whether psi is less than A or greater than B is Q diamond purified P. And by the lifting, we can have this is greater than or equal to tilde omega, the sample complexity of purified P. And then this is given by square root sample complexity of P, and by direct calculation, this gives square root d over delta. Okay, so the summary, the message is quantum sample lower bounds imply quantum query lower bounds. And our second part is a quantum samplizer, that is to do the inverse, do the reverse, that is we consider how to convert a quantum query algorithm to a quantum sample algorithm, and this further generalized the sample to query lifting. Okay, so first, this is the definition of quantum samplizer. A quantum samplizer is a mapping samplize star star star, and is a converter such that for any precision delta and quantum query algorithm A with queries to U and quantum state rho, and there is a unitary operator U rho such that the upper left corner is rho over 2, satisfying AU rho is delta close to the samplized version of AU with many copies of rho as the input. And here we use E rho to denote a quantum channel implemented by samples of rho, and it looks like this. And here E rho is the channel, and rho is used to implement the channel. And we show that there is a quantum samplizer such that AU uses Q queries to U. Then the samplized version of AU with samples of rho, and also the delta is a precision parameter. It uses S samples of rho, which is Q square over delta. And here, taking delta is a constant, for example, 2/3, gives the quantum sample to query lifting theorem stated before. So now we introduce the implementation of the sampleizer. Our idea is, the first is that suppose we have many samples of rho. The first step is to use density matrix exponentiation. We can implement a unitary e to the minus I rho. And then we can use the quantum singular value transformation to do the logarithmic function, and we can obtain a unitary operator whose upper left corner is rho over 2. And finally, we can show that we can approximately implement some controlled unitary U with upper left corner rho over 2 and its inverse to precision delta in diamond norm using tilde O 1 over delta samples of rho. And the implementation here is, suppose that you have a quantum query algorithm whose circuit is G0, U1, G1, blah blah, and here G0, G1 to GQ are quantum elementary gates, and here U1 to UQ are the queries, either a controlled U or controlled U dagger. And using the construction here, we can convert this quantum query algorithm as follows. For each UI, we can approximate delta over Q approximate UI by a quantum channel EI with tilde O Q over delta samples. And here, there are Q queries, so the total number of rho is Q times each implementation Q over delta, and this results in a sample complexity of Q square over delta. Okay, now we show a simple example how the quantum sampleizer is useful to a real problem. We consider the von Neumann entropy estimation. That is, we want to estimate S rho, this is von Neumann entropy, equals minus trace rho log rho. And the question is, how many samples of rho are sufficient? Our circuit, our idea looks like this, and this is an Adama test. And this circuit first perform a Hadamard test, a Hadamard gate, and a sample of rho, and the rest are zero states. And then we perform a unitary V here, and V with upper left corner approximately equal to minus C log rho over 2. And here C is a parameter to be determined later. And here is we perform another Adamard gate and do the measurement. The measurement outcome is X, and we can show that the probability that X is equal to 0 is this, and which is related to the von Neumann entropy. And if we repeatedly do the measurement and compute the mean, then we finally obtain an estimate of the von Neumann entropy. Specifically, we can choose C to be this, and as there is a polynomial p such that minus c log x over 2 and px is very close, and px is constant bounded, and the degree of p is not that large. And in short, p rho can be approximately equal to minus c log rho over 2. So given this, V can be implemented using Q queries to U row. Here U row is have upper left corner rho over 2. And the way to do this is first we have U row here, the upper left corner is rho over 2, and we do the quantum singular value transformation, and we can obtain P rho over 2. And because P is a good polynomial, which is approximately equal to minus C log rho over 2. Okay, and then V can be delta approximated by the samplizer with certain parameters, and here then we have the sample to implement. The V here is Q square over delta, and here Q is the degree of P, and delta is the precision parameter. Okay, the idea looks like this. So then V is approximately implemented by a samplized version of VU rho with many samples of rho, and the precision parameter is delta here. And we can repeat this circuit. We can finally obtain an estimate of von Neumann entropy by computing the expectation of X. So after some analysis in this approach, we can show that for a d-dimensional state rho, d square samples of rho and d square numbers of 1 and 2 cubic gates are sufficient to estimate the von Neumann entropy to within any constant additive error. And this cubically improves the prior time complexity by Acharya, Issa, Schender, and Wagner. And their time complexity is d to the 6, and our time complexity is d squared. And here we also show another example, that is to estimate the Tallis entropy. Tallis entropy, the Q Tallis entropy is defined by 1 minus trace rho to the Q over Q minus 1. And here, the blue part, trace rho to the Q, is the key value we want to estimate. Okay, and here we also use a similar idea by the ADMA test. But the difference is that here the unitary V is approximately equal to a unitary that is with upper left corner C times rho over 2 to the Q minus 1. And here C is a parameter to be determined later. And we also do a measurement. The outcome is X. The probability that X is equal to 0 is given by 1 plus 2 to the 1 minus Q times C times the trace of rho to the Q over 2. And that's why this measurement outcome is related to the value of trace rho to the Q. And we can perform this many times, and we can finally estimate trace row to the Q. Okay, so to this end, we can choose C, and then we have a polynomial P such that Px is approximately equal to the C times x cubed minus 1, and Px is constant bounded, and the degree of P is not that large. And then we can implement V using Q queries to U row. Here Q is the degree of P. And similarly, we can do the quantum singular value transformation, and we transform a unitary operator U row with upper left corner row over 2 to a P row over 2. And by the choice of P, we have that this is approximately equal to C times row over 2 to the Q minus 1. And finally, V can be approximated by samplized version of this, which uses S samples, which is Q squared over delta, and Q is the degree of P, and delta is the precision parameter. So after some analysis, we can show that for a d-dimensional state row, O1 samples of row and the tilde O1 1 and 2 qubit gates are sufficient to estimate trace row to the Q for Q greater than 1, and thus we can estimate the Q Tallis entropy, SQ row. And we know that the samples of row to estimate the Tallis entropy is independent of D, and this exponentially improves the prior result with sample complexity poly D. And we also give a third application, and this application finally produces an optimal approach with sample optimal approach for pure state trace distance and fidelity estimations. And this also shows that there is a problem that can be solved by the samplizer with, that achieves the optimal sample complexity. Okay, so what we want is to estimate the trace distance and the fidelity, and when rho and the sigma are pure states, and here in the pure state case, the trace distance is 1 square root 1 minus bra phi and cap psi square, and the fidelity is the bra phi cap psi absolute value. The folklore approach to this task with an additive error epsilon is based on the swap test, as shown here. And we can this actually gives a sample complexity 1 over epsilon to the 4. And this is because you can do the measurement here, x, and x equals 0 with probability 1 plus the squared fidelity over 2. And you can perform it many times and do the taking the average value, and then you can show that this approach results in a sample complexity of 1 over epsilon to the 4. And our question is, can we do better? And yes, we can by samplizer. The key observation is this circuit. That is, let R phi be a reflection operator about phi, and upside is the reflection operator about psi. And this is a phase estimation quantum circuit. And here, we can do the phase estimation of the unitary operator R phi R psi on the quantum state phi, even though phi is not an eigenstate of R phi R psi. But never mind, we still perform the phase estimation. And we can show that using Q queries to R phi and R psi, it gives an epsilon estimate of the fidelity and the trace distance. And note that R phi and U phi has upper left corner phi over 2, can simulate each other with a constant overhead. And therefore, we can samplize the phase estimation procedure to precision delta equals very small value but constant, using S samples of phi and psi, which is Q squared over delta. And here Q, and we recall that Q here is 1 over epsilon. And that's why we finally obtain a sample complexity of 1 over epsilon square. And here we also know that for pure states, the polylogarithm factors can be removed from the sample complexity. So there's no tilt. And finally, after some analysis, we can show that 1 over epsilon square samples of phi and psi are sufficient to within additive error epsilon. And this sample complexity is also optimal. And there are other applications, for example, fidelity estimation to well-conditioned quantum states, and estimating the L alpha distance between quantum states. And also, recent developments show that this can be used to do the quantum singular value transformation for quantum channels. Okay, let's summarize what we have introduced now. We review a novel connection between quantum query complexity and quantum sample complexity. For quantum via a samplizer, and we can show upper bounds and we can show lower bounds. For lower bounds, we can show quantum query lower bounds for several problems, quantum Gibbs sampling, entanglement, entropy problem, and so on. And we can also show quantum sample complexity, including the estimation of von Neumann entropy, and Renyi and Salis entropy, and trace distance and fidelity, and so on. The part 1 is the lifting. This is for the lower bounds. We can show new quantum query lower bounds from quantum sample lower bounds. And part 2 is a samplizer. We can show upper bounds. We can show new quantum sample upper bounds from quantum query lower bounds. And this bridges 2 different quantum complexities. Yeah, so our questions here are some to be think in the future. Can we find some more applications, either for lower bounds and upper bounds? And also, is there a classical analog of quantum lifting method? At this moment, we only know that this can be done quantumly. We don't know is there any classical analog. And can we find other relationships between quantum query complexity and the quantum sample complexity under some other definitions? And here, in our case, we define quantum query complexity to be the Q diamond. And that is a special case of the quantum query complexity. And question is, can we define other type of quantum query complexity and make them related to each other? Yeah, and that's it. Thank you very much for your attention.
Thank you very
Questions are
much.
welcome.
So I have one question. So Could you back to the fidelity estimation?
Okay.
So,
Do you mean this?
fidelity estimation, yes. So in that case, you have some assumption. We are available R phi and R psi. That unit is available as an oracle.
Uh,
So this is the
yeah, yeah,
assumption.
yeah. No. We don't have this assumption. This is a step of our algorithm, and in this step, we assume that we have R phi and upside. However, afterwards, we can show that this R phi and the upside can be implemented by only samples of phi and psi.
Only sample phi.
Yeah, we can.
Oh,
That is R phi and the upside can be implemented by phi, by samples of phi and by samples of psi.
okay.
So
So then
given
what is the
this,
assumption? Assumption is you have a n copy of psi and n copy of phi.
yeah, we have many copies of psi and many copies of psi. Yes,
Oh,
and yeah, our problem is how many copies of phi and many copies of psi are sufficient to estimate something.
of course, if one of psi is known and only phi is unknown, in that case, the problem is quite easy. If you know the psi, we know psi, and unknown state is only phi. In that case, the problem is much easier, almost trivial. In the
Uh,
PSS case.
No, actually, it is not the case. Even if you know only that is, we have two states, psi and phi. If you only know one of them, but the other one is unknown, the problem is still difficult. And we can show a lower bound that is omega 1 over epsilon square to this problem, even if one state is kept 0 and the other is unknown.
Why? Because it is easy to make that kind of projection to that state. So then you can calculate that probability. So this is very efficient method.
Yes. But
So in this case, so that problem quite easy. But if the state is a mixed state, the problem more difficult. For
for your
example,
case, for your case, if you have phi known, then you can measure it in the computational basis. However, the measurement outcome has probability. I think it's the probability, the square, the fidelity, and
yes.
after that you still have to compute the trace distance by this formula. This formula you have to take the square root. So because of the numerical analysis, the sample complexity is still not optimal.
Huh? Numerical. Oh.
If you are interested, I can show you why the analysis sample complexity is like this.
Square root. I see.
That is, if you use a direct measurement, the sample complexity is still 1 over epsilon to 4.
Okay, I understand.
Thank you so much.
Okay. Maybe is there a question? So is there a question in Nagoya side?
No, no from Nagoya.
Nice to meet you.
Nobody. So okay, thank you very much.
Thank you so much.
Now we want to proceed to the next speaker. Maybe almost time.
Yeah, from Nagoya. Yeah. He's,
Yes, next speaker is Wu Xianwang from Nagoya University. Okay, Hussein, are you ready to talk?
Okay. Hello, can you hear me?
Yes. So the next speaker is Hussein Wang. The title of this talk is Quantum Digital Signature on Single Qubit without a trusted third party. So please start.
Okay. Hello, everyone. I'm Wushen Wang. I will present a recent quantum digital signature protocol based on single qubit without a trusted third party. And it can obtain quantum theoretical information security under some reasonable assumptions. This is a joint work with Professor Masahito Hayashi. The motivation for us to research this topic is digital signatures is an important primitive in cryptography, and they are fundamental for authenticity. However, many quantum signature schemes still rely on a trusted third party. This will break the decentralization. And we know that the decentralization plays an important role in some cutting-edge applications. For example, in blockchains, the decentralization is the most important property. In this figure is the schematic for the task of digital signature. We can see that there are two parties, Alice and Bob. Here, Alice is the signer and Bob is the verifier. The task is that Alice sends the message and signature pair to Bob. Then Bob verifies if the message is really sent from Alice. Then we formally define the quantum digital signature. A quantum digital signature protocol has three phases: key generation phase, signing phase, and verification phase. In key generation phase, Alice performs an algorithm skgen with the input of lambda to generate a private key sk, where lambda is the security parameter. Subsequently performs an algorithm pkgen with the input of sk to generate a quantum public key rho pk. Then she sends the public key to Bob. In signing phase, Alice performs the algorithm sign with the inputs of sk and m to generate a classical signature SGN, where m is the message. Then she sends the message and signature pair to Bob. Finally, in verification phase, Bob performs an algorithm ver with inputs of pk, m, and SGN to generate a binary output 0 or 1, where 0 corresponding to the case of rejecting the signature and 1 represent accepting the signature. And in this table, we can see why our protocol is more secure than existing studies. The papers 16 to 18 are quantum authentications based on quantum physically unclonable functions. However, these schemes cannot realize the function of message transmission. And papers 20 to 25 are quantum digital signatures with a trusted third party. So these schemes, in these schemes, the decentralization is destroyed. And papers 26 to 30 are general quantum digital signature frameworks. However, in these frameworks, the adversary's computational power is limited. On the other hand, they didn't propose a specific protocol. Next, we introduce the forging attack. This is a famous attack and is the most important attack in digital signature model. And this is related to our security analysis. There are three parties: Alice, Jack, and Bob. Alice sent a message M and signature S. At this moment, Jack intercepts the message M and signature S. Then he generates a new message M prime and signature S prime, where the message M prime is not equal to M. Then Jack sends this message signature pair to Bob. We say that if the forging attack succeeds if Bob accepts Jack's signature. Otherwise, the forging attack fails. Our protocol satisfies the following four requirements. The first is a trusted third party is not needed. The second is it satisfies theoretic K epsilon unforgeability. This means that a party in the protocol holds K copies of the public key succeeds forging attack with at most the probability of epsilon. And the third is undeniability. That is, the signer cannot make the verifier to reject the signature. The final one is expandability. That is, the cost of the protocol does not increase so fast as the length of message increases. In the following, I will introduce our protocol in detail. We assume that the message needed to be authenticated is an L-bit message M. Then our protocol uses the following four algorithms. In the algorithm skgen, the output is a family of bijk and vijk, where I is an element in 1 up to L, and J is an element in 1 up to lambda. K is an element in 0 and 1. And bijk is a uniform random variable in X and Z. Here X and Z are Pauli operators. And bijk is a uniform random variable in 1 and -1. These are the eigenvalues of the Pauli operators. Then in the algorithm pkgen, the output is a family of hij, where hij is one of these four quantum states. The algorithm sign output a family of bij mi and bij mi. Finally, the algorithm will output 1 or 0. First, in key generation phase, Alice performs the algorithm skgen to generate a private key sk, and then she keeps it. Subsequently, she performs the algorithm pkgen to generate a public key. That is the family of hij. Then she sends each of them to every party. Here, Alice becomes a signer and Bob becomes a verifier. Then in signing phase, Alice performs the algorithm sign to generate a message and signature. Then she sends the message signature pair to Bob. Finally, in verification phase, the verifier Bob makes the quantum measurement for the family HIJMI under the basis BIJMI respectively. If for all IJ, the corresponding measurement result is equal to BIJMI, he accepts the signature, otherwise he rejects the signature. In the following, we analyze the security against unforgeability. To theoretically analyze the security performance resisting unforgeability, we need to calculate the specific probability that a malicious party, Jack, succeeds the forging attack. And the probability is given in the theorem 1. We see that there are 2 parentheses, and for each of the parentheses, the first number represents the number of copies of the public key, and the second number represents the probability that Jack succeeds the forging attack. Where for 0 copy case, Jack does not measure the quantum public key. So in this case, the calculation for the probability is not difficult. However, for n copy case where n is no smaller than 1, the calculation is much more difficult. So to solve this problem, we need to introduce a new theorem. And if an adversary colludes with n minus parties, he can hold at most n copies of the public key. To calculate the probability that the adversary succeeds forging attack, we should calculate the minimum error probability in state identifications. Because in this case, Jack may measure the n copies of the public key to obtain extra information. And we apply covariant group method in this section. For 1 qubit, we know that a qubit is one of these four states, 0, 1, minus, and plus. And here we define 2 new bases, E0 and E1, which are the eigenvectors of Pauli operator Y. And then we can reconstruct the 1 qubit state as a state family Fx, which is a covariant with the group Z4. And for n copy case, we need to unfold the quantum state under the basis in the symmetric subspace. Finally, we also can obtain a state family covariant with the group Z4. And our target function is 1 minus Fn. The value of this target function represents the minimum probability that checks cannot pass the verification phase. And here X represents the ideal quantum state and X hat represents the measurement outcome. Here the pi X is the QVM. And the error function represents that if the ideal state is X and the measurement outcome is X hat, then the probability of that Jack cannot pass the verification phase is R. So after constructing the optimum POVM, we can conclude the theorem 2. That is the value of the minimum value of the probability that Jack cannot pass the verification phase. And then we can calculate the probability in theorem 1. And we also make the numerical calculations for the probability of succeeding a forging attack in the case of n equal to 5. That is, Jack has 5 copies of the quantum public key. In this figure, the x-axis represents the security parameter lambda, and y-axis represents the probability. We can see that the probability goes to 0 as lambda increases. Okay, thank you.
Thank you very much. So, is there any question or comment in our side? No comment from our side.
One question.
Okay, please.
So other than the forging attack, is there any possible attack pattern?
Yes. We introduce another attack here. No. One extra attack is denying attack. That is, the signer makes the verifier to reject the signature. However, in our case, we can ensure this security because after the signature is sent by Alice, then Bob does not need to communicate with Alice anymore.
So she cannot, change anything. She already sent. Oh, okay.
Yes. But looks like the third problem looks like trivially resolved from the formulation, I think. So then we need to discuss the second problem. From the construction, third kind of attack cannot be made.
Sorry, what's your second question?
No, comment. So that kind of that kind of attack cannot be made, essentially. Yes. Undeniability due to that construction. Because already signer made signature. So
Then signer cannot do anything.
due to that construction, that third problem never happened, I think. Okay, is there any question or comment? So, okay, thank you very much. So we want to move to the final speaker. So final guy is me. How to pronounce? Final speaker is
Hello?
yes, me, Gray, Jin. Yeah.
Yeah, can you hear me clear?
Yes. You are not from here. So.
Yeah, because of the typhoon immigration, like the train has been canceled, and yeah, apologies for that.
Cancel.
Yeah, it's just a very special case, but I really want to go to the university, but maybe next time. Okay. Okay, so can everyone see my slides clear?
Yes, from Nagoya, it's okay.
Okay, thanks. Okay, so hi everyone. My name is Minrui Jin, and I'm currently a PhD student at Hong Kong UST Guangzhou, study with Professor Xin Wang. And firstly, I would like to thank Professor Masahiro Hayashi and all the colleagues at CUHK Shenzhen for organizing this wonderful quantum science workshop. I'm very glad to have this opportunity to present our new design in quantum machine learning that has been accepted for this year's QTML at Singapore. And this is also a joint work with Erdong Huang, Xiao Shi, and my supervisor Qing Wang, and the leader of the Tencent Quantum Lab, Professor Shenyu Zhang. Okay, so here is the outline of my presentation. So at first, I will briefly deliver a preliminary of the quantum machine learning. And I noticed that most of you guys may not be familiar in this field. So I will introduce the concept and the framework of quantum neural networks, as well as the dynamic algebra of quantum neural networks with some examples. And I will also shortly state about the recent theoretical development on the connections between the dynamic algebra and the QNN's trainability issue, so-called the Baron-Platons issue. And in the second section, I will introduce our quantum recurrent embedding neural network, including the circuit framework and the algebraic structure of it. Then we will apply our model to solve quantum supervised learning tasks for classifying quantum data. And focusing on that, we then demonstrate the trainability of our model, and will showcase that the polynomial lower bound on the gradient variance with respect to the dimension of the data register. We will also illustrate the numerical results of our theorem. And at last, we will run some ideal simulations and showcase that our QREN model can achieve competitive accuracy for detecting symmetry-protected topological phases from embedding the dynamics of the physical systems. Okay, so let's start with the first one. So in the classical neural networks, there are three main parts of the model, namely the input, the hidden, and the output layers. The data vectors are inputted and the information flows through the hidden layers until it reaches the output. And if you're familiar with the classical neural networks, you know that the hidden layer contains all the tunable parameters and the activation functions so that the total neural network can approximate any kind of continuous functions and build up the suitable correlations between the input and the output layers. In the current stage, quantum neural networks is kind of a resemble model to the classic scenario, which can be represented as a parameterized quantum circuit with fixed initial state. So the model contains a data processing layer, colored in green here, and the data embedding layer, colored in yellow here. And the data processing layer always often contains multiple parameterized gates with the tunable parameters encoded in. The raw data are encoded in the data embedding layer, represented as a unitary operator embedded in the networks. So this model is also called the quantum data re-uploading framework. And at the end of the circuit, a measurement will be applied, which usually followed by some simple classical post-processing method for better task performance. Okay, so to give an explicit algebraic representation of quantum neural networks, a concept called dynamic Lie algebra were firstly introduced in quantum control theory. So given a quantum neural network expressed in the generator form, as shown in this first equation here, a dynamic Lie algebra of this QNN is a real linear space spanned by a collection of these skew permission generators, which are closed under the Lie bracket operation. So notice that here in the compact finite case, there's a theory proved that the dynamic Lie algebra of any quantum neural networks can always be decomposed into a direct sum of simple Lie algebras. So why we need to study DLAs? Well, in the field of quantum neural networks, there is a fundamental trainability issue, namely the barren plateaus. That is, an average gradient of the trace form loss function can exponentially decay with respect to the number of qubits if we apply the uniform initialization of the model. So recently, literatures have unified the occurrence of EP by finding out the explicit connection between the gradient variance and the dimensionality of each decomposition simple Lie algebra. In particular, if a circuit is deep enough, usually polynomially deep, to reach a unitary 2 design on the subgroup generated by the QNN, then an explicit formula of the gradient variance can be derived for the trace form function. So here I provide some of the small examples which are usually used in QNNs. So let's see, let me put the laser. So here, the first one is a very simple local P2C parameterized quantum circuit. And in this case, you can see that the Lie algebra span, the dynamic Lie algebra is simply just a direct sum of SU2. In the second place, if you get a match gate circuit, which are usually used in some optical circuits or the devices, you get a generator which spans the whole SO2N. And it is still very small compared to the last one, which is the universal circuit. And of course, the dynamic Lie algebra now is the entire SU2 to the power of n. So with this in hand, we can build up an inside that the high dimension of each decomposition subalgebra, the high possibility to encounter barren plateaus while training the model. Okay, so these have inspired us to design actually this created a very inspired, like the field and the questions in this field, that can we design a new paradigm of quantum neural networks which are both trainable and powerful, but also can avoid barren plateaus. And we try to resolve this question, this problem, by designing this quantum recurrent neural network. Under this situation, then we can, under certain situations, we can actually prove that this model can avoid the barren plateaus issues. Okay, so here comes the circuit model of our QRENN model. The model is made of two registers. Firstly, the first one, the first M qubit is called a data processing register, and the last N qubit is called the data embedding register. These two registers can be connected with an embedding map G, and the processing layer representing the local optimized circuit are applied solely on the processing registers, which the number of qubits or the M is usually restricted. While in the same time, the data usually encoded in the system Hamiltonians are embedded into the network, while the control evolutions here. So such a structure is usually appears in the famous, for example, the QSVT or the QPP framework, also the LCU framework, which build up the interaction between the processing qubits and the data. And we build up this framework because we think that to have a quantum neural network with suitable quantum advantages, we have to take insight into the advantages quantum algorithm design. And at last, there's also a local measurement at the end of the network to extract the processed information from the network. So interestingly, when we assume that the encoding Hamiltonians form an abelian algebra for any input data x, the DLA of the network can be nicely and have a simple form as shown here, with the number of decomposition space depends on the number of distinct joint eigenspaces of this abelian algebra. So clearly, now the dimension of each decomposition subalgebra only depends on the number of qubits in the processing register. So if you can restrict n, it can be possibly escaped from the Baron-Plateau issue. Okay, now we have the model. So what's next? It's time to find out the power of our model. So in particular, we focus on solving the quantum supervised learning problems, which occupies a significant sector in this field as well. We consider classifying the quantum systems based on different features carried by the system Hamiltonians. And notice that the information about the quantum system is completely stored in this Hamiltonian. So usually in the quantum applications, we can deal with the quantum evolution to find out the properties of the system. Of course, the first challenge is caused by the loss function evaluation. So in the traditional quantum supervised learning, the MSE, or the mean square error loss, as shown in this first equation, is settled for the optimization. So however, this loss function, you can see that contains the second order terms of the trace form, which is very hard to analyze and inefficient to evaluate in practice. We take the inspiration from quantum hypothesis testing and design a new total loss. Here involves only the first order terms of the trace form. And in particular, if we can construct suitable POVMs here, denoted as M1 to MK, we can easily compute the loss values and perform the gradient analysis. So based on the new laws, we can now showcase our main theory on the traceability of our new model in solving quantum supervised learning tasks. Specifically, we consider the binary classification problems and define two local POVMs as the projections onto the +1 and -1 eigenspaces of all Z operators acting on the processing register. So these POVMs are local POVMs. And thanks to the mixing time theory from previous literature, for polynomially scaled layers of QREN models, the uniform initialization of the circuit can then achieve a two design of the compact group generated by the net. So with this assumption, we can come out the main theory. If we restrict the number of qubits in the processing register scales as logarithm of the number of qubits in the data register, suppose the initial state rho n has sufficiently large overlap, actually the polynomial large overlap acting on the abelian algebra spanned by the encoding Hamiltonians, then the gradient variance with respect to any tunable parameter in the model can have a polynomial lower bound regarding the number of qubits in the data embedding register. One point here is that the sufficient large overlap from the initial state is sometimes a bit tedious. However, in many QSVT-based algorithms, this is a reasonable assumption from if we have a priori information of the task. And moreover, there are recently several warm-start methods which are issued to resolve this initial overlap problem. So I will provide a sketch of proof of this main theory here. From now, we focus on the specific encoding Hamiltonian being directly encoded data and recurrently into the different layers of the model. Let's start with taking the derivative of the loss function with respect to any parameters in the network and derive the gradient in the summation form here. Then notice that by taking the assumption of two design, we can average the gradients over the group, which the linearity and the trace of the commutator then gives that the average gradient vanishes to 0. And from the formula of variance, we now only need to compute the average of the square of the loss gradient. By using the property of the split Casimir operator, which computes the explicit formula for the second moment integration over the group using the projection onto each decomposition subalgebras, we then derive the lower bound for the variance here at the bottom of this page. And we find out that the lower bound depends on the Frobenius norm of the POVMs, and also the overlap of the initial state with respect to the data Hamiltonian. So since the norm of our constructed POVMs are logarithmic with respect to the number of qubits in the data embedding layer, this bound can be actually polynomially lower bounded by the small n here. Okay, so we also provide numerical demonstrations by taking the gradient sampling experiments. So in particular, we have investigated 3 typical data sets, including classifying the poly, the involutory, or the dynamic, or the diagonal Hamiltonians from the set of random permission matrices. And for each data set, we prepare the training set by generating 50 data with corresponding features respectively, and another 50 data are generated from sampling higher unit rates. We then embed this data into the network as shown in the circuit diagram here, and taking the POVMs defined as before and all the assumptions made as stated in the theorem, we then sample 500 random initial parameters to derive the gradient variance for each n in the embedding register. So as we can see here, from the first diagram, all the results from the 3 data sets diverge from the exponential decay sketched in the logarithm scale. We have also plotted the tendency of the variance with respect to the number of slots in the model. And in the second diagram, we can observe that a rapid decay to the fully mixing phase of the gradient variance value as we reach a polynomial scale the number of slots in the network. These have proven that our network matches the mixing time theory from previous literatures. Okay, so apart from that, it is very interesting to think about whether we could extend the application of our model to some other physical problems. And in particular, we focus on the detectation of symmetry-protected topological phases problem, which plays a very important role in the condensed matter physics. And for example, given the cluster Ising model here with periodic boundary conditions, the Hamiltonian of the system can be expressed in this explicit form. And some research have also showcased that there is a phase transition point when lambda equals to 1. So we designed an experiment for detecting this phase transition point with n equals to 8 qubits by firstly constructing a training set with labeled phases of 0 and 1, where 0 represents the cluster state phase and 1 represents the anti-Fermionic space. And we sampled lambda values from 0 to 2 to construct the training set, also the testing set. We then train the model by inputting train the model on the training set, and then test the model on a 560 points generated in the same way. So let's see what happens. Well, from our numerical results, we can find that this model can work surprisingly well on detecting this SPT phase transition. So in particular, in this numerical result, we have fixed that the number of qubit in the data processing register to 1, and the initial state, which is fixed to 0 state, product with a 4 plus state. And interestingly, we find that we can, after training, we can achieve a 98.72% accuracy on these 516 testing data, which have get a compatible performance compared with the usual classical SPT phase detection method. And also in the case 2, we have taken some investigations on the performance, the effect of performance with respect to the training size. And we can find that with the training size increases, we can, firstly, the performance can increase rapidly. And then when the training size keep go up, it becomes slightly reduced. I think this is because that the training becomes much harder because you are training the model on a larger training size, and it might comes a lot of like low local minimum points to make this training much more harder. Okay, but overall, this training results is pretty competitive compared with currently existing methods. So here's the conclusion. In this talk, I have briefly introduced the recent development in quantum machine learning, and I have taken the result from the Lie algebra to the quantum neural networks. And we also described that, also introduced the outcomes from how to connecting the dynamic Lie algebra theory to the baryon plateaus issue. And in the second section, we have briefly introduced our quantum recurrent neural network, which is inspired by the quantum circuit architecture. And we showcase theoretically and numerically showcase that this model can somehow avoid baryon plateaus in quantum supervised learning. And the applications showcase that this model can achieve a great success in SPT phase detection. And to that, I think that's the end of my talk.
Okay, thank you very much. Is there any question or comment on our side? No?
Yes, ma'am.
Thank you for the talk. Can I ask about the SPT detection?
Okay, sure.
So in that case, you not test the ground state, but you consider Hamiltonian only, and then you time evolve the certain fixed input state by that SPT Hamiltonian, and then check the output. Is this correct?
Mm-hmm. Yeah. So the initial state is fixed, and we just encode and embed the Hamiltonian evolution into the network, and then taking a measurement to produce the prediction. Yeah.
Yeah. Okay. So what I'm curious is, usually SPT phase is a property of ground state. So, only low energy part of the Hamiltonian matters. But in your case, the Hamiltonian evolution is acting on, not energy eigenstate, but more like, just product state. So it could be like far from ground state. So I wonder why that step can capture such low energy physics.
Oh, yeah, that's a very good question. So, guessing that this, so from our experiments, we have a guess. Actually, you're right. The initial state is very important in this model. So, one guess for your question is that this all plus state for this clusterizing model, all plus state might be good for extracting the eigenvalues. I mean, I think it's very close to the ground state of the Hamiltonian. So in that case, you have a great chance to extract the spectral information from the local measurement. So in that, with this in head, you may have a chance to detect the phase transition because you just got more information from this input state.
I see.
Yeah.
Is digitize some perturbation to the input states and then how the the date changes, success probability changes?
Say it again.
Can you digitize any kind of different input states, for example, breaking the symmetry in SPT phase or just random local, random tensor product states as an input or something like that?
Right. So yeah. So I think for like SPT phase detection, you usually the usual way to make the detection is to perform the localization measurement, right?
Yes, yes.
And at the phase point and the phase transition point, there's usually a localization or the entanglement breaking thing. So that's why we think that a product state might be useful. And if that's like a global, more like a global properties of the system, this product state might not be not a good choice. And in that case, maybe you can choose some, the entangled state. But currently, we do not have a general method to find out the good state. But I think it's a very good future direction to explore. Yeah.
Okay, thank you.
Okay, thank you very much. Any question or comment? So maybe there are no further comments. So now I want to close today's session. So thank you very much.
You're welcome.
Thank you. So tomorrow we start the same time as this morning. So thank you very much.